Dear students, in the last lecture we have completed transformer modeling part, and today's lecture we will go with modeling of step voltage regulators. Before going to the voltage regulator modeling, let us see the function of voltage regulator. So, we know that the voltage along the feeder will go on decreasing. So, drop along the feeder will go on increasing as loading increases. So, whenever there is no load condition, if these loads are not there, you can see that voltage both the points will be same. However, whenever there is loading on your feeder, there will be current which is flowing to the feeder, and which will basically there will be drop across the feeder. So, voltage which is reaching at consumers which are connected at the far end will experience lower voltages. However, there is limitation on how much voltage can decrease at particular consumer end. So, say in our case, if it is there is a 10% plus minus variation in voltage if it is allowed, in that case if normal voltage or nominal voltage if it is 240, then voltage variation allowed is from say 264 to 216 to 264. So, its voltage all over the system, the voltages should be between 216 to 264. Now, during loading condition, during no load condition, suppose voltage is something like this. So, whenever during loading condition, the voltage drop will increase and voltage will reach to some lower values. So, it may cross your limitation, that is 216. So, it will go below that particular level. So, in that case what we can do, we can increase the voltage at source point itself, and that increment in voltage can be done by using OLTC of the transformer, or if the OLTC is not available your transformer, you can use extra regulator which basically regulates the voltage at the secondary side of the regulator. So, if the voltage of the secondary side of transformer is say 240, then by using voltage regulator I can make the voltage at the secondary end of the regulator say 264, which is I have shown it here. Though even though there is drop across the feeder, we can bring the voltage within the limit. Okay. So, there will be this blue colored line which I have shown, these are nothing but your service drops. So, there will be some drop which is happening in service connections, those drops are shown in blue. So, we need to regulate these voltages within the band. So, we should know why we need to keep these voltages within that particular limit, because if the voltage variation is allowed, say under voltage or upper voltage, there will be improper or less efficient behavior of your equipments. So, basically what will happen is whatever your lighting load is there, it will not illuminate properly, as well as if there are motors connected, they may run slow or they may run fast during under or over voltage conditions. So, operation of your equipment will be improper, as well as there will be some losses which are happening into the feeders, they may increase or decrease. So, it will be actually less efficient operation. Also, we know that many sensitive loads they are basically connected by your UPS systems. So, UPS system is basically consist of inverters, and these inverters are designed such that during the under voltage or over voltage they will cut off from the supply side. So, during that condition your sensitive loads will be getting from battery, and they will keep on draining the battery, and sometimes battery will get exhaust of the charge, and in that case your sensitive equipments will be out of power. So, this can happen if prolonged over voltage or prolonged under voltage across your sensitive load, and in that case inverters will be cut off from the supply because of under voltage or lower voltage conditions. So, tripping of sensitive load may happen during under voltage and low voltage. Let us see what are the problems with over voltage. So, these are two which are shown in red dots, basically problems of over voltage conditions. So, during the over voltage condition, your equipment will get stressed more. So, there is a possibility that equipment failure may happen and it will damage the equipment. Also, during the over voltage condition, your transformers they will be taking more magnetizing currents and your no load losses will be increasing. So, your transformer will show or take more magnetizing current, which will lead in more no load losses. Because of under voltage, so this is the problem which under voltage. So, under voltage will affect the load which are basically constant power kinds of load, say induction motor, which will be considered some kind of constant power load. In that case, if to keep power constant, if voltage is decreased, in motor has to increase the currents, and if the voltage is decreased more, in that case current to the motor will increase, or basically it will increase the copper losses into the motor, and there are many chances that motor will get burned. So, there is overheating the motor because of more copper losses, or burning of induction motor may happen due to under voltage conditions. So, these are various effects of under voltage or over voltage on your equipment. So, because of that, we need to keep your voltages under the strict limits of plus minus 10%, or in some state they use plus minus 6%, or some state they use plus minus 5%. So, depending upon the requirement, we need to keep these voltages within those bands. Now, let us see what are the options available, or what are the techniques available using which we can regulate these voltages over your distribution system. So, one important voltage regulator component is actually your on load tap changing transformer. So, we know that then generally your taps will be provided on high voltage side of your transformer, and by increasing or decreasing the taps, we can change the voltage at the secondary side, and depending upon the voltage requirement at other end of the feeder, we can increase or decrease the tap and regulate the voltage at secondary end. So, we are already seen the modeling of transformer. Then there are actually bus step voltage regulator, which are basically connected at the bus. These are nothing but auto transformer or transformer which are connected in auto transformer fashion. We will see how we can model and how they regulate the voltages in next few slides. Then there is voltage boosters. These are nothing basically two transformers, one is connected in series, another connected in shunt fashion. So, two different two winding transformers which are connected, one is connected in series, another is connected in shunt fashion, and by regulating the voltages across series winding, we can control the voltage. So, this is actually voltage booster. Then there are actually feeder voltage regulator, basically they are called as induction regulator, and these are nothing but induction motors, where your stator winding and rotor windings of these induction motor, they will be connected in series, and induction motor will be in steady state position, means it will not be running. However, depending upon the phase, or you can say angle of the voltage requirement, we can change the position of your rotor. So, in this case, the voltage across the stator, and say this is voltage across the rotor. So, total voltage which is getting regulated, which is given by this one. So, by then by changing the angle, we can by rotating a rotor little bit, we can change the angle, and then in that case your voltage will be this one. So, by changing angle, so we can again decrease also. So, in this case, if this is your stator voltage and rotor voltage, we can by rotating 180 degree, we can make it in opposite direction, which will basically decrease the voltage across the feeder. So, we can increase or decrease voltage at the along the feeder by using these induction regulators. And then there are actually to regulate the voltages along the feeder, fixed or switched capacitors are also used. So, this switched or fixed capacitor we will see in next few lectures. Now, in this case we will most concentrate on what is called as bus step voltage regulators. So, let us see how they work. As I told you, main function of your step voltage regulator is to regulate the voltages at the feeder end. So, this says your feeder end, this is start of the feeder and which is basically connected by say regulator, and say there is a transformer here, and we want to regulate the voltages at this one. So, function of this one we want to regulate at this. Okay. So, let us say we want to regulate voltage at this end is say 240 volts, but exact 240 keeping exact 240 volt will not always possible because there will be some bandwidth of the regulator. So, say we want to keep the voltages of this particular bus within the limit of say 242 by 238 range. So, lower I can go up to 238 and higher I can go up to 242. So, whenever voltage is going beyond that I need to regulate using this particular regulator. So, to do that they use what is called as line drop compensator circuit. Before going to line drop compensator, we will see this various terms. Voltage levels is basically this voltage level which is 240 volts, then bandwidth, the allowed variance of voltage at load center from set voltage level. So, this set voltage level is 240 and allowed voltage level is 238 to 242. So, in that case bandwidth is actually your 4 volt bandwidth. Then time delay. So, when voltage is changing here, it will change with respect to time. Let us say voltage is changing like this. So, this is your voltage and this is your say time, and this is your lower band on voltage, say this is your upper band on the voltage. So, because of say decrement in the load at this end, so this load is connected at this place which is say decreasing, and because of decrement in the load the voltage at this bus is say increasing. So, let us say voltage is increasing like this, it is within the band. So, we do not have to worry. Now, here the voltage has gone beyond the limit which you have specified. So, we need to operate the regulator at this point. Okay. However, what will happen is there will be some time delay and then regulator will operate. So, here the voltage has gone up, however, the regulator has operated at this particular point. So, the time difference between these 2 points where the tap change operation is called for, because we need to call for tap change operation at this point. However, your actual execution of command is happened at this particular. So, this is called as time delay, and this time delay is required, however, because we do not want frequent operation of your regulator, because there will be always small changes in the current which will basically change the voltage at the feeder end, and for those each transient changes in the current we do not want your regulator to operate. Means I can say that here the voltage this current is decreasing and voltage was going up, however, suddenly suppose some load has come, then what will happen is here the voltage will start dropping. So, since this drop is happening or it is voltage is coming within the limit before your time delay set time delay, here the your operation of regulator will not happen, because this change in the voltage is basically happened due to transient change in the current. So, for that we do not want to operate your regulator. So, there should be always some time delay specified with regulator operation. So, as I told you, this operation is carried out using what is called as line drop compensator. So, this is your line drop compensator circuit. We will see what is inside this, and we are taking signal corresponding to current using CT and fed to this one, and similarly we are getting signal proportional to your voltage using PT, and it is given to line drop compensator circuit. So, this is your potential transformer, this is your current transformer, and signal corresponding to your load current will be taken by CT, and voltages at regulator other end will be taken it by PT, and this line drop compensator will decide voltage need to be increased or decreased, and then it will given to the voltage relay. So, it will given to the voltage relay, and this voltage relay will be given time delay, because as I told you time delay is required to avoid the frequent operations of the regulator or chattering of regulator. So, this is your voltage relay which gives signal. There will be some time delay circuit, and after that this signal will be given to what is called as motor operating mechanism. And this will give signal to your regulator. So, this will be actually given signal to the regulator, and this regulator will operate, or its step will be changed depending upon the voltage step down or step up is required. So, there are two types of regulator. They call it as type A and type B regulator. Almost they are similar, however, they just differ in their connections. So, as I told you, the step voltage regulators are basically auto transformer, and they are having load tap changing mechanism. So, in case of type A regulator, you are having this circuit here, something like this. So, as I told you, it is auto transformer which are basically two windings, one is called as common winding and one is called as regulating winding. So, these are two windings. So, basically this is your regulating winding where we need to use taps. So, these are various tap positions on this one, and here this is common winding, and then there will be selective switch which is connected here, and then there will be secondary side. So, this will be your VL load voltage, this will be your VS primary voltage, the current which is coming is IS, current which is going to load say IL, voltage across this winding is say E1, voltage across the regulating turns which are coming into circuit is say E2, turns say N1, turns of this say N2, and current through this winding it will say I1. Directions will decide how they vary, and say these windings are connected such that the dots are at the top. So, the dot connection is because they depend upon how windings are wound. So, windings are wound so that dots are say here. So, in this case suppose this connection is connected, this terminal or this selective switch is connected to this terminal. So, in this case what will happen is simplified diagram of this will be something like this. So, here we are having sorry. So, this is again your VL, this is your VS, and this is your IS current which is going on. And if you see where the dots are coming, for this winding dot is coming somewhere here, and for this winding the current will be going like this and this like this. So, initially if for this winding is coming dot at the top. So, basically whenever current is entering, the dot is coming somewhere here, and then it is going so start of the winding we are getting dot, and then it is connected to VR terminal. So, dot is coming somewhere here. So, this dot is here and this dot is here, and your current IL will be here. So, we know that always if the current is entering to some dot, it should leave to the other dot. So, here since the direction of current is something like this IL, which is going out of the dot, okay, then this current should come towards dot. So, direction of I1 will be something like this. So, this is your E1, this is your E2. So, I can easily write your Vs or VL will be equal to your E1 minus E2, right, and then your Is will be Is plus I1 will be equal to your IL. So, in that case I can write Is will be equal to your IL minus I1. Okay. Now, when so what will happen is in this case your VL load voltage will be lower than supply voltage, because supply voltage is corresponding to your Vs and E1, they will be equal because that they are connected same. So, in this case your this will be equal to Vs minus E2. So, E2 will get voltage will get subtracted. So, therefore, in this case your VL will be lesser than your Vs, right. Since VL is less than Vs, we can call this terminal as EL terminal, because when we are putting switch on this particular terminal, it is actually lowering your voltage. Now, if you see if switch is connected to this particular terminal, okay, in that case your circuit will be like this. So, when this so this other terminal I can call it as R, because it will be used for raise. I will explain how it is coming to raise. So, this is when the switch is connected to L is this L position, and when it is connected to say R position. So, when this terminal here, in that case again I am just drawing your regulating winding, and then this is common winding, and this is your VL here, and this is your Vs here. Direction of Is and IL, they will be as specified. However, if you see here, this dot will be here only for this winding. However, dot of this winding, so is starting, and then this dot will come here. So, dot will be at the end of this winding. So, dot will come somewhere here in this case. So, in this case it is E1, this is E2. Current direction, if you see, in this case current is entering to the dot. So, in this case current has to leave the dot. So, current direction will be this one. So, I1 direction will be something like this, IL direction which is entering the dot. So, I can easily write in this case VL will be equal to addition of, because they are in same direction. So, E1 plus E2, and your IL will be equal to, or you can say Is minus I1 will be equal to your IL. So, in that case your Is will be equal to IL plus I1. So, by connecting your regulator to R terminal, we can increase the voltages as second. So, here you can see that your VL will be more than Vs. So, you are raising the voltage from source voltage, that is why this terminal I am calling it as a raise R terminal, and here here when it is on this side, switch is on this side, we are actually lowering the voltage, which you have seen here when VL is becoming less than Vs. So, that is why I call this switch as switch L. So, this particular condition which I have shown it here, this will be for switch position which is position R. Now, let us see B type regulator. The construction is similar, however, only the connections are different. In this case also there are two types of winding. One is again we need regulator winding with tap positions, and then one common winding which is same. Then this is your VL terminal, and here we are taking this, and this will be connected to your selector switch. So, which may be connected on this side or it may be connected on this side, this terminal. And then as I told you, there will be taps on this regulating winding, so that we can increase or decrease voltage from set position, and your supply is connected to this particular tap. So, it is just opposite of that A type of regulator. So, this is your Vs, this is current Is, and the current which is leaving here I am calling it as IL. Again here this is E1, this voltage across this regulating winding terms which are coming in circuit, it is E2, N1, the turns are N2 here. Now, in this case also, as I told you, there are two positions possible. One position I am calling it as a position R and L. Let us see why I am calling this position as a position R. So, in this case also, if you dots are something like this dot is here and this dot is here. So, let us say your position is on R. So, this terminal is connected here. So, I will just remove this. So, it is connected like this. So, if you draw this diagram here, it will be something like this, where this is your Vs and this is your Is, this will be IL, VL. So, this voltage is your VL. Now, if you observe the dots here, so when Is is coming from this side, I will just take different color. So, you understand, say the current is coming here and then going in, and then from this side both the current is getting added and then it is going like this. So, dot, if you observe this drop, it is coming opposite side of the winding. So, in that case a drop is coming somewhere here, and this drop is dot is here. So, this is your voltage E1, this is voltage across this is E2, number of turns are N2, here the number of turns are N1. Now, you can easily see that your E1 by E2 will be equal to your N1 by N2, which will be equal to your I2 by I1. Basically, this current I am calling it as I1, and this current say I2, which is I2 is equal to Is, both currents are same. So, I can say it is Is divided by I1. Now, if you see the voltage Vs will be equal to E1 minus E2, both are in opposite direction, dots are opposite direction. So, voltage will be E1 minus E2. Now, your voltage E1 will be equal to VL, because VL and E1 voltage they are same, this voltage and this voltage it is same. So, VL minus, and then your voltage E2 will be your N2 minus N1 times E1, which is basically again VL equal to VL. So, VL minus N2 by N1, E1 and E1 and VL they are same. So, I can say VL here. So, it will be 1 minus N2 by N1 into VL. So, you can see that Vs will be lesser than VL. In this case, Vs will be lesser than here. So, since this particular condition is happening, that is why we need to put this connection as a raise here. So, this particular terminal will be a raise terminal, because you are getting VL, the terminal voltage VL, which is more than Vs. And this particular term, which is 1 minus N2 by N1, I am calling transformation ratio or transformation ratio of the regulator AR multiplied by VL. So, where AR is nothing but 1 minus N2 by N1. Now, let us see what is the relation of currents here. So, since if you can see here, this current IS is actually coming towards dot here. So, this current should go away from dot. So, this current direction will be like this. So, I1 direction will be something like this. So, in that case I can write another equation. So, we have got this first equation here, from that we have got this term here. So, I can say this 2. So, your IL will be equal to IS minus your I1. So, we are getting IL will be equal to your IS minus I1. Now, this I1 we can write in terms of IS. So, in this case I can write IS or you can say will be equal to N1 by N2 into I1, or I can say I1 will be equal to N2 by N1 into your IS. So, this I1 I can just replace by IS will be equal to N2 by N1 into your IS. This will be equal to 1 minus N2 by N1 into IS. So, I can just write IS will be equal to 1 divided by AR into IL, because this will lead to IS will be equal to your IL divided by 1 minus N2 by N1, and this we have defined it as a AR. So, this term if I write it AR, it will become actually this equation. So, IS will be equal to 1 divided by AR multiplied by your IL, and when this terminal is connected to L, it will be opposite, where we are connecting this to say L. So, I will just erase it. Now, in this case I am connecting it to L. So, in that case your dot is here. So, this dot, since this circuit is not coming into picture, this dot will come somewhere here, and if you draw equivalent circuit of this, it will be, this is regulating winding, then this is your common winding, and then we are having this terminal here, and dot will appear here, this dot will appear here, then it is IL, voltage VL which is across terminals, this is Vs, and input current is Is. So, in this case, since this current is entering to the dot, this current should leave the dot. So, leave the dot means actually it should be, direction should be like this, basically directions this way. So, you can say in this case this current is leaving the dot towards inside the winding. So, it should actually inside the winding it should flow towards dot. So, here it is leaving the dot. So, it should flow towards the direction of the current will be something like this. So, I1 will be directed like this and Is will be directed inside winding like this. So, this is your E2 E1 and E2. So, I can easily write in this case your Vs will be equal to E1 plus E2, and by using same philosophy I can just say Vs will be equal to 1 plus N2 by N1 into VL. So, we can get these relations. So, which will make Vs will be equal to nu AR, which I am getting it here, multiplied by VL, and same relation in this current relation also I can get IL will be equal to Is plus I1, because if you apply KCL at this node, your IL will be equal to, because both these currents are coming toward the node. So, IL will be Is plus I1, and if you simplify this, it will be 1 plus N2 by N1 into Is, which will make your AR into Is. IL is equal to AR into Is, and this implies Is will be equal to IL divided by AR. So, we have got these relations, and depending upon where it is connected, lower or raise. So, this is your terminal which basically raises the voltage, and depending on which is connected it will decide how much raise we want. Similarly, when it is connected to L, it will lower the voltage, and depending upon which terminal it is connected, it will lower that much particular voltage. So, basically in this connection we have got two equations, which is basically Vs will be equal to AR into VL is one equation, and another equation which is Is, which is equal to IL divided by AR, which is second equation, and this AR will be equal to 1 minus plus N2 by N1, because when it is raise we are getting minus sign, as we have discussed in slide. So, here we are getting minus sign when we are setting it is in raise position, and in case of lower position we are getting plus sign here in both the cases. So, it will be, that is why I am writing minus plus instead of plus minus, and this decides your how much voltage is getting increased or decreased. So, if you can compare these voltages, so basically we want ABCD parameters here. So, we know that ABCD parameter we want Vs voltage, supply voltage, which is in terms of A VL plus B parameter into IL, and Is we want which is equal to C into VL plus D into IL, which is say 3 and 4. And if you compare this voltage, these equations with respect to this equation, I can say your A will be equal to AR for B type of regulator. We are all these things that we are derived for B type of regulator. B parameter, because since there is no term which is related to current here into this particular equation, so your B parameter will be equal to 0. In this case there is no term. Second equation, if you compare with respect to this 4 equation, term related to C is not there. So, then that case C also I can say 0, and your D will be equal to 1 divided by AR. Similar analysis if you do for A type of regulator, you will get just opposite, because we know that both the type they are just oppositely connected. So, for A type of parameter this regulator, your A parameter will be 1 by AR, B will be 0, C will be 0, and D will be AR, because they just both are oppositely connected. Now, if you see this AR I am saying it is equal to 1 minus plus into N2 divided by N1, and this N2, that is turns on regulator winding, they are variable because we know that the turns are changing depending on the tap position, and we want voltage variation to be in plus minus 10%, right. So, the number of turns in regulating winding will be 10% of turns in the common winding. So, say if there are say in common winding, if there are say 1600 turns, then turns in regulating winding they will be say 160, because only 10% variation we are doing using the regulating winding, right. And this 160 regulating terms, we are taking 16 taps out. So, there is plus 16 taps minus 16 taps. Our plus minus we are doing just by raising or lower switch by that selecting switch. So, there will be 16 taps we are taking it out from it. So, 16 variations will be available. So, since we are taking 16 tap, so per tap number of turns will be 10 turns. So, this will also, because 16 divisions we are making. So, per division or per tap there will be 10 turns, right. So, when your regulator on normal tap means 0 tap, then we can see that number of turns of regulating winding will be 0. So, AR will be equal to 1 minus or it will be whatever it is, minus plus, it's both are okay. So, in that case this ratio will be 0 divided by 1600. So, it will be just 1. When tap is say plus 1, in that case your AR will be equal to 1 minus, for tap 1 we are adding 10 turns of N2 winding. So, there will be 10 here divided by 1600, which comes around 1 minus 0.00625 into, since one tap is there, so I can say write 1. When on it is on tap 2, so AR in that case it will be equal to 1 minus, now since there are 2 tap position, it will add 20 turns of regulating winding. So, N2 will be then 20 divided by 1600. So, it is nothing but equal to 1 minus 0.00625 into 2 taps, it is equal. So, so per 10 turns the voltage variation which is per unit voltage variation which is coming, which is 0.00625 when we are considering 16 tap positions. Okay. So, in generalized way I can write this AR will be equal to 1 minus plus 0.00625 multiplied by your tap position. So, if you know the tap position where the your regulator is lying, you can easily find out this AR, because it AR will be just tap position multiplied by 0.0625 plus minus it should be added or subtracted from 1. So, when we want to raise the voltage in case of B type regulator, you need to use minus sign, and when we want to reduce the voltage or negative taps, you need to use plus sign. So, that is why minus plus. So, minus is used for raising the voltage at the secondary side, and plus is used to decrease the voltage on secondary side. So, in summary of today's lecture, we have seen why voltage regulation is required, because this under voltage or over voltage condition will create lot of effects on your equipments of your consumers. So, your voltages of the distribution system should be kept under strict limits of say plus minus 10%, or some cases it is plus minus 6% also. And we have seen those effects on various component, how under voltage and over voltage effects on various equipments. Then we have seen various techniques of voltage control. So we have seen voltage can be controlled using on-load tap changer. We have seen step voltage regulator, voltage boosters, induction regulators, or switched and fixed capacitor. Out of these, we are seeing step voltage regulator into this particular section of chapter. And then we have seen how we can model single phase regulators, and we have seen that there are two types of regulator, type A regulator and type B regulator. And from the first principle of auto transformer connection, we have derived ABCD parameters of type B regulator. Next time we will see how we can model 3 phase connected regulators. Thank you.